Good afternoon, lads and ladies. Welcome back to Calc 1. Today we are going to wrap up the last bit of the material that is going to be on your second exam. So today we are going to cover applied optimization, and then Friday we're going to review. Remember, the test itself is on Monday. That is the 2nd of November, next Monday. Excuse me. So without any more wasted time, I will flip over to the document camera and we can get moving. Pink has been working okay. I guess we can stick with that. Sorry, my breakfast plate is still sitting here. Okay. So today is the 28th of October. And today we're going to talk about applied optimization. Which I think is not section 4.6 if I remember right. I think the sections kind of jump around here a little bit. So let me take a quick look. Yeah, it's 4.7. So for those of you who intend to go into industrial or systems engineering, applied optimization is the main thing. It's a huge field. It's a really big deal because, of course, anybody who has a large machine or manufacturing plant or any sort of large-scale physical operation wants to be able to do that as efficiently as possible. And that usually means minimizing your costs, so finding a local or absolute minimum, and subject to some constraints. Before we get into the material, though, I want to remind you, especially for anybody who's coming in or watching this online, exam 2 is Monday, 11/2 during normal class time. And a few people have been kind enough to send me emails already reminding me of their accommodations or any special testing situation that they're in, whether you're traveling or you're unwell, or the DRC has been slow responding to you, or the DRC is working with you, but you want to do something other than the normal thing, whatever it is, anything at all that you would like me to know or you think is important for the test, you should communicate that to me, and communicate it to me as quickly as you possibly can. Another little reminder, study guide 2 is up. I did not get it up on Monday. That was my fault. I was very busy grading some other classes' materials, but I did post it early this morning. So your second study guide is up, and you need to write and scan solutions as soon as you can. So remember, to get the grade for study guide 2, if you look in the syllabus, a meaningful chunk of the grade for this class comes from the study guides. To get the grade for study guide 2, it is not enough to just solve the problems in WebAssign. You need to write out your solutions and scan them, submit them to Canvas. The due date for that, the latest you can do that, is the day of the test. But ideally, you will scan and submit those solutions, or at least some of them. If you don't get all of it done early, that's fine. But ideally, you will scan and submit those solutions before the day of the test, so I can look them over and give you some feedback, because that's the point of the study guide. The point of the study guide is for you to show me your work on these problems so that I can look over your work and give you some advice that will be helpful for the test. I understand not everybody takes advantage of that, and that's okay, but my strong advice is to work on the study guide as soon as you can, scan and submit those solutions as soon as you can. That way I can give you some feedback that you can incorporate into the rest of your studying. That feedback is only helpful for the test, of course, if you get it before the test, and I cannot get you that feedback before the test unless you get me your work before the test. So in order to be as helpful as possible, I recommend that you start the study guide today and then submit it, sometime over the weekend, preferably not like 11:59 on Sunday night. But if you do that, I will still do my best to get you some feedback before the test begins. All right. I think that's all the announcement-y stuff. So let's begin applied optimization. So optimization comes from the word optimal or ideal or perfect. And the game is to get some function minimized or maximized. And usually there are some constraints. Jonathan asked, what about homework 9? Homework 9 is due according to the normal schedule. Is there an issue with homework 9 that I'm not aware of? Yeah, no, due according to the normal schedule on Monday. Of course, if you end up needing that extended, you can request it, but I would advise that you finish it like the study guide as soon as possible. So these optimization problems are, for the most part, real world min and max problems. I'm just going to write the word stuff because I don't quite have room for the word problems. So maybe I have like a certain amount of fence material. I've got like 1,000 feet worth of fence material, and I want to enclose the most area I can as I build a fence wherever, in my property. Or maybe I want to make a box, and I want this box to have as much volume as it possibly can, but I want to use the least material possible. That sort of situation. These don't tend to be terribly hard problems, but I want to just give you a rundown of how they feel. And think usually because they're word problems, the challenge is not so much the mathematics, but getting from the word problem to the mathematics. And I'll just grab some examples here that we can work with. The book has this nice guideline here. You should read the problem and make sure you understand it. What is it you're being asked to do? Drawing a picture is almost always an important step here, just like the related rates problems where you need to draw a picture to really understand what's going on and label things. And then the third step here is the labeling. So assign a symbol to each of the quantities, give names to the variables that are in play. The fifth step that they list here is an important one. This will show up in a lot of our problems. Oftentimes, you'll end up with like two equations. You'll have one equation that represents the thing you're trying to minimize or maximize. And then you'll have another equation that describes some constraint, like I only have, maybe I want to enclose the most area. So my area function would be the one I'm trying to maximize, but I only have so much fence. So an equation, describing how much fencing material I have to work with would be my constraint. And often you'll have to solve the constraint equation for one variable and then plug that into the thing you're trying to minimize or maximize. This is to get rid of a variable so that you then just have a function of one variable which you can find the min or max of. So let's go ahead and grind out example 1 here. They say, and I'll write this down and then switch to the dot cam. We have 2,400 feet of fencing. And we want to build a rectangular region along a river. No fence is needed along the river. Presumably, whatever we're trying to fence in here cannot swim. We want to know what's the max area. We can enclose. So I'm going to flip back to the doc cam now, but take a look at some of these pictures. So they've drawn a few possible situations, like where you've got 2,200 feet of fence parallel to the river, and then 100 feet of fence on each side that is perpendicular to the river. Here you've got a very narrow, like very long but very short region, and the area in that case is 220,000 square feet. And if you compare that to these other ones, they both use the same amount of fence. If you add up the perimeter here, all of these add up to 2,400. But the middle guy has 700,000 square feet area, and the far right guy here has 400,000 square feet area, both of which are considerably larger. So there's a bunch of different ways we could configure this paddock, and we want to know what's the way that will maximize the area. So I'm going to flip back to the dot cam now and solve this for you. All right, so I've summarized the information here. We have 2,400 feet of fence to build a rectangular region along a river. No fence is needed along the river. What's the max area we can enclose? So I'm going to draw my river. And then I'm going to imagine my little fenced in region over here. The fenced in region is a rectangular region. So this side is the same as this side, but remember I don't need fence along this side. And also this side is the same as this side. So the parts that are actually fenced here, I'll draw in these blue dashes so we have some color contrast. The parts where we're actually using fence are the bits with the blue dots there, the blue dashes. The thing I want to maximize is the area. And the area, A, well, it's a rectangle, so it's the length times the width, right? It's X times Y. It's the product of those two dimensions. And we're subject to the constraint that I only have 2,400 feet. So the perimeter has to be equal to 2,400 feet. Now I should use all of that fencing, right? If I want to enclose the most amount of area and I've got 2,400 feet of fencing, it doesn't make sense to use anything less than 2,400. So that constraint is the perimeter, which is X plus Y, or X plus 2Y equals 2,400. Are we all comfortable with the setup? Are there any questions about what we've said so far or the two equations we wrote down, where they're coming from? Okay, so if you look just at this function, A equals xy, A there, the area, is a function of the two variables, x and y. And in this class, Calc 1, we don't know how to work with functions of two variables. We only know how to maximize or minimize functions of a single variable. And so we need to solve our constraint equation for y. That will allow us to plug an expression involving x in here, and that will give us a function we can work with. So I'm going to come back to my constraint, and I'm going to solve it for y. This is the same as saying 2y equals 2400 minus x. And then if I divide both sides by 2, that's the same as saying 1200 minus 1/2 x is y. Okay. Now, plugging this into our area, we get the area purely as a function of x. So I'll write a of x is x times y, and y is 1200 minus 1/2 x. And that, if I distribute my x, I get 1200 x minus 1/2 x squared. So this is the function that I want to maximize. I would like to find the absolute max for this area function. Any questions about how we got this far? Okay, well then if my goal is to find the absolute max of this function, this is actually a quadratic. We could find it just by finding the vertex. This is the sort of thing that you learn how to maximize way back in college algebra, but now we're in Calc 1, so we can take the calculus approach to maximize a of x. We treat it like any other min-max problem. We calculate the derivative, a primed. Here the 1200x will differentiate to 1200 minus 1/2 x squared differentiates to just minus 1/2 times 2x, which is x. So a of x has critical numbers, really just one critical number, when a primed of x is equal to 0, which is equivalent to saying 1200 minus x is equal to 0, which is equivalent to saying 1200 is equal to x. And we can verify that this is a max by making a number line using our first derivative test. So this will be a number line for a primed. I'll put 1200 here. If you test something to the left of 1200, like 0, then a primed of 0 is 1200 minus 0. That's definitely positive. So a primed is positive to the left of 1200. And if you test something to the right of 1200, like 1201, a primed of 1201 is 1200 minus 1201, which is -1. In particular, it's negative. This tells me that the area is increasing as x gets bigger and bigger until you get to 1200, where it turns around and starts decreasing. So this has to be a local max. And in fact, it's an absolute max. If you think about the graph of A of x looks like, it's a parabola opening down. It's the only max. And the function is increasing everywhere to the left of it, decreasing everywhere to the right of it. So this is also absolute. So the area is maximized when x is 1200. And then we can solve for y. This means we go back to our constraint equation. Remember the relationship between x and y is given here. So since x plus 2y has to be, what was it, 2400. That 1200 plus 2y is 2400. Just plugging in for x here, the x value I found that maximizes. I can then subtract over, and I get 2y is 2400 minus 1200. Which is the same as saying 2y is, well, 2400 minus 1200 is 1200. So y itself has to be 600. So the dimensions that maximize the area are x is 1200 and y is 600. And the max area itself is 1200 times 600. Now 12 times 6 is 72. So this is 72 or 720,000 square feet. Okay, so there are several versions of this question, or several things I could ask you for. I could ask you, what are the dimensions that maximize the area? And you would tell me 1200 by 600. Or I could ask you, what is the max area? And then you would tell me the max area is 720,000. This is a good example of a problem. It's a prototype problem. It's very simple, but it's got all the pieces that even more complicated problems like this have. So I'd like you to take a second, reflect on what we did, make sure your notes are clear, and then ask any questions that you have. Are there any pieces here which feel strange? Anything here we'd like to talk about a little bit more? Anything we'd like to ask about?
No, I'm good, thank you.
Anybody else? No, mostly good? Sure. So we drew a picture. We wrote down the function we're trying to maximize and the constraint. The constraint here came from the amount of fence we had available. We solved the constraint equation for one of the variables and plugged that back into the area function to give us the area as a function of one variable. Then we differentiated and found the maximum of the area function. And then we just took those values and plugged them back in. Josh asked a good question. If this wasn't a parabola, how would, so here when I plug in for my constraint, I recognize that this is a parabola opening down, so the max is an absolute max. In that event, Josh, if there are multiple maxima and minima that you need to consider, you have to treat it like one of the problems from the previous section, from section 4.1, where in order to identify an absolute max or an absolute min, you have to compare all the maxes and mins to each other, as well as the value of the function at any endpoints you may have. So you have to treat this like one of those find the absolute max problems from section 4.1 if the situation isn't such that you can tell right away it's an absolute max. Most of these applied optimization problems, you won't have a horrible time with that, but it's worth saying that, yeah, sometimes it won't be obvious which max or which critical number gives you the thing you want. And in that event, you'll have to compare the outputs from all the possibilities to choose the optimal one. So let's look at another example. Okay. Cylinder holding 1 liter of oil. That's okay. We can do this. All right. So maybe I am an oil company, and I know I need to sell containers of oil that are 1 liter in size. And I want to minimize the amount of material I need to do that. So find the dimensions of a 1 liter cylinder which minimizes the amount of material. Used to make the cylinder. I should say hollow cylinder. Right, so it's like a can. Right, think like a soup can. Back in the 50s and 60s, oil actually came in cans, even up through the 80s in some places. So we want to find out, the aluminum or whatever it is I'm using to build this can. It costs money. I know I need to sell oil in 1 liter quantities. So I want to know, how can I make this cylinder cost the least amount of money to manufacture? And the answer there is, well, you got to use the least amount of material. So let's picture our can. It's a hollow cylinder, a cylindrical shell, looking something like this. It has a radius, r, and a height, h. The volume of a cylinder, the volume for anything that's like this, where if you slice it, the cross-section is always the same. So like no matter where I slice this, the cross-section would be a circle. So to find the volume, you take the area of a cross-section, the area of this circle, and you multiply by the height. So that's pi r squared, because that's the area of the circle that makes up a cross section, times the height. The other thing that's at play here is the surface area of the cylinder, right? So in reality, this thing has a top, it has a lid. The sides are all made of stuff. The bottom is solid as well. And my art skills are really being put to the test on this. Right, the thing's made out of stuff. So if we want to find the surface area, you have to imagine like cutting and unrolling the cylinder. If you do that, you've got the circle on top, the circle on the bottom, and then if you cut and unroll the middle, that forms a little rectangle. So the surface area, the amount of material I need to make this thing, I've got two circles of radius r, and I've got a rectangle whose height is h, but what is this dimension of the rectangle? You don't have to necessarily tell me a formula, but can you tell me a word that would tell you what the dimension of this rectangle is? This is kind of the middle part of my soup can unrolled. Very good, it's the circumference. It's the circumference of the circle on the top, because if you pop the top and bottom off and then cut and unroll the cylinder, the width of the resulting rectangle has to go all the way around the circle at the top, which means that the width is the circumference of the circle. What's the formula for the circumference of a circle?
2 pi r.
Very good, 2 pi r. Pi times the diameter, 2 pi times the radius. Okay, so the surface area, I'll call it S, is pi r squared plus pi r squared, the top and the bottom, plus h times 2 pi r. Which one of these is the thing I'm trying to maximize or minimize, and which one of these is my constraint? One of these things is fixed, the other one is variable. Is it the volume or the surface area that I'm trying to maximize or minimize? So it's not the height. I'm just asking between the volume and the surface area. Yeah, I want to minimize the surface area, right? Because I want to minimize the amount of material used, and the volume is fixed. Good. So we know that the volume has to be 1 liter. And we want to minimize the surface area. So my constraint is going to come from the volume. And the thing I'm trying to optimize is the surface area. Now, since the volume is 1 liter, I know that pi r squared h is 1. And I'm going to leave off the units here. This will allow me to solve for h, which I can then plug into my surface area equation to get a function of a single variable. So if I divide over by pi r squared, I get h is 1 over pi r squared, because pi r squared h was equal to 1. And we can plug this in to our surface area to get the surface area as a function of a single variable. So I'll write it as S of R. S of R is 2 pi r squared plus h, and h is 1 over pi r squared times 2 pi r. So I'm just taking this equation, which I have for S, and where there's an h here, I'm plugging in what I know h must be. The notation on the left-hand side is function notation. It's not S times R. I'm writing S of R to emphasize that it's a function of the single variable R. If you don't like writing the of R, or on the previous problem, the A of X, you can leave it off. But it's a nice bit of notation to let your reader know that you're thinking of the surface area as a function of the radius. All right, algebra time. 2 pi r squared is 2 pi r squared, nothing to do with that. But here, I can cancel the pi's. I've got an r upstairs and an r squared downstairs, so I'll end up with 2 times 1 over r. Right, like I can cancel the r and the square. So now I need to differentiate. So S primed of R, the 2 pi is a constant, it will come along for the ride. R squared differentiates to 2r to the 1, plus 2 is a constant, it will come along for the ride. 1 over r is r to the negative 1. So he has derivative negative 1 times r to the negative 2. I can clean this up. 2 pi times 2r is 4 pi r, plus 2 times negative 1 times r to the negative 2 is minus 2 times 1 over r squared. Is everybody following the differentiation? Maybe on the side here, I'll add the thing we used. 1 over r primed is r to the negative 1 primed is negative 1 r to the negative 2. Just a power rule. So to continue from here, I need to find the critical numbers for S. I want to find the absolute min for S. So we must find where S primed of R is 0 and where S primed of R is undefined. To do that, I'm going to have a common denominator between these two pieces. Slide another paper under here because my pen is acting up. So S primed. This piece has denominator 1. this piece has denominator r squared. So I'm going to multiply by r squared over r squared here. And I get 4 pi r cubed over r squared minus 2 over r squared. Which is 4 pi r cubed minus 2 all over r squared. And in fact, I can factor a 4, or I'll factor a 2. Let's do it like that. That's 2 times pi r cubed minus 1 over r squared. 2 times, sorry, this should be a 2 pi. Yeah, sorry about that. So after putting together with a common denominator, we factor out a 2 from the top. That's all. So S primed will be 0 when the top is 0, and S primed will be undefined when the bottom is 0. So critical numbers for S of R are, let's see, R equals 0 isn't actually in the domain. R equals 0 makes S primed undefined. But isn't in the domain of the original. So we don't need to worry about him. And then setting the top to 0, we can divide both sides by 2. And then we could try to find a way to factor this. That's an option. It could be force factored as a difference of cubes, but since I'm only interested in the real solutions, I might as well do it the college algebra way. Let's add 1 to both sides, then divide both sides by r cubed, or sorry, divide both sides by 2 pi. So we get r cubed equals 1 over 2 pi. And then we'll take cube roots on both sides. So r is the cube root of 1 over 2 pi, or just 1 over the cube root of 2 pi. Everybody with me so far? Now this equation here is a polynomial equation of degree 3. So there are actually 2 other solutions, but they're non-real solutions. They're complex numbers, non-real complex numbers. So we don't need to stress about those. You can solve this the way someone would in high school, right? Just adding over, divide by the constant, take cube roots. So we just have this one critical number. We hope it's a min, but we should check. Here's my number line for S primed, and I'll plot my one critical number here. It's 1 over the cube root of 2 pi. To the left of this is certainly 0, right? 2 pi is positive, so the cube root of 2 pi is positive. So something smaller than this would be 0. We can plug 0 into S primed. If we do, oh wait, no, 0 we can't plug in, can we? Ah, shit. Because 0 is not in the domain. And this number is quite small. So let me come back to this. Over here, let's say we'll test r equals 1, because 1 is definitely bigger than this, right? 2 pi is about 6, so certainly bigger than 1. the cube root of a number bigger than 1 is bigger than 1. So we can test r equals 1 to the right. If I plug r equals 1 in here, s primed of 1, I get 2 times 2 pi minus 1 over 1 squared, which is, well, let's see, 2 pi minus 1. Again, 2 pi is about 6, so this is about 5. 5 times 2 is about 10. This is in the neighborhood of 10. In particular, it's positive. So s primed is positive over here. What could we test to the left of this? That's a little bit harder. Let's see. Well, we said that 2 pi is about 6. So the cube root of 2 pi, well, it's going to be smaller than 6. So I could test r equals like 1/10. Since 2 pi is about 6, the cube root of 2 pi has to be smaller than 6, which means this whole thing is bigger than 1/10. S primed of 1/10 would be 2 times 2 pi times 1/10 cubed minus 1 all over 1/10 squared, which is 2 times 2 pi times 1/10 cubed. 1/10 cubed is 1/1000. 10 times 10 times 10. So that's 2 pi over 1000 minus 1 all over 1/10 squared, which is 1 over 100. 2 pi over 1000 is very small, right? Again, 2 pi is about 6. So this is like 6 over 1000, which is definitely smaller than 1. So when you subtract 1 from it, no doubt that will be negative. So indeed, over here, we are negative. Another option, if you don't like this, and I admit this is a weird number to work with, so finding something just to the left and right of it is hard, you could use the second derivative test. You could calculate s double primed and verify that when you plug this number into s double primed, you get something which is positive, which means the function is concave up at that point. And if you have a horizontal tangent at a point where you are concave up, that has to be a min. So this fellow is indeed a min. And like the previous problem, since we're decreasing everywhere over here and increasing everywhere over here, even though this isn't a parabola, it's not at all quadratic, it only has the one point, one critical number. You're decreasing everywhere to the left, increasing everywhere to the right. That means this has to not only be a min, but it's the local and absolute. Min. So r is 1 over the cube root of 2 pi. This minimizes the surface area. They asked us for all the dimensions of the can. The other dimension that we need here is the height. So again, to find the other dimension, you go back to your constraint. Our constraint was the volume being equal to 1. So I can come back here and say, since h is 1 over pi r squared, we know, or we find that h has to be 1 over pi times 1 over the cube root of 2 pi squared. And that can be cleaned up considerably. I've got a 1 over pi, and then I'll flip and multiply by the reciprocal of this guy. So that's going to be 2 pi under the cube root all squared. It's not a pretty number. There are some things we could do to it, but for my money, I would just leave it like this. That's 2 pi raised to the power of 2/3 divided by pi. And yes, you could combine the pi's. You could treat the top as 2 to the 2/3 times pi to the 2/3. And then take pi to the 2/3 divided by pi to the 1. We know that this is an absolute minimum because the function is decreasing everywhere to the left and increasing everywhere to the right. In other words, it only has one turning point. If you're decreasing everywhere, decreasing, then increasing everywhere, increasing, and you never turn around again anywhere else, it's not possible for you to have any other minima. So try to think about the shape of the graph. Regardless of concavity, we're decreasing everywhere to the left, and we're increasing everywhere to the right. So the graph has to go down, 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 turn around, go up, 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 up. So this has to be an absolute min. The only way for this to not be an absolute min is if there was some other min which was lower. But that would require another critical number. And we don't have any other critical numbers. That would require another turning point. In fact, at least one other turning point. Does that make sense? Yeah, kind of think of it like a parabola, right? Even though this, again, this is not a parabola, the function being that we're discussing here, I can graph this for you. Where was our simplest form of R prime? Now, I'll graph it as it is there. I'm going to use the variables y and x instead of s and r. This is 4 pi x cubed minus 2 all over, oh, God damn it. All over x squared. Well, the scale here is a little wonky, but our domain is just things to the right of 0. Did I type that right? 4 pi x cubed minus 2 over x squared. Let's see, I'm trying to find this here. Somewhere down here, we've got our local minimum, which is an absolute minimum. Oh, this is S prime. I'm sorry, this isn't S. We need to graph S. Yeah, we're looking for the derivative of S, or the maximum minimum of S. So what was S? S was, as a function of R, S was 2 pi R squared, so 2 pi X squared, plus 2 over X. Here we go. Yeah, so here's our function. We're only considering positive values of R. So I'm only considering x's which are bigger than 0. And we'll say y runs from 0 to 100 or something. And here we go, right? So everywhere in our domain, we're decreasing, then we turn around and we are increasing. So even though this shape isn't exactly a parabola, it's definitely not, it's some other weird wonky shape. If you're only decreasing to the left and you're only increasing to the right, then this min has to be an absolute min. Other points where we started. So r equals 0 looked like it might have been a critical number for this function, but it's not in the domain. This function is undefined when x is 0, when r is 0. So we don't have to worry about any of those. It is possible that in these problems you'll encounter multiple critical numbers. Just neither of the examples we've looked at so far have any. All right. So I'm going to zoom out for a minute and let you guys fill in any bits of your notes that need filling. Did I answer that last question where you said, I thought you mentioned there are other points? Could I ask for a little clarity on that? What do you mean? Or what is it you're referring to that I said? Oh, we're good? Okay. Yeah, it is possible that there are other critical numbers. From a certain perspective, this one does, right? This numerator has 3 numbers that make it 0, but only one of them is a real number. The other 2 are non-real complex numbers. Maybe that was the thing that was sticking in your head. I'm going to bump this up in 5, 4, 3, 2, 1. So once we find the R value that minimizes the surface area, in this problem, they asked us for the dimensions that minimize the surface area, not for the minimal surface area itself. So the dimensions that minimize the surface area are a radius of 1 over cube root of 2 pi and height of 2 pi to the 2/3 over pi. If we wanted to know what is that minimum surface area, then yes, we would plug this and this back into the surface area function. So sometimes we want to know where is the max or where is the min, i.e. for what inputs do we get the max or the min? Sometimes we want to know what is the max or what is the min. And in this case, if you wanted to figure out what is that minimum surface area rather than what are the dimensions that produce it, you would plug these dimensions, this R value and this H value, back into our surface area function. Okay, let me see how we're doing on time. We've got enough time left, I think, for one more quick one. And I'd like to show you guys one of these problems that is not necessarily originating from the real world. So, first derivative test, we've talked about these, right? Oh, this is nice to think about. So absolute extrema, this is actually what I was just saying, right? If you have a critical number and f prime is positive everywhere to the left of that and negative everywhere to the right of that, then that is not only a local min, but it's also the absolute min. So if you're decreasing everywhere to the left and increasing everywhere to the right, then regardless of what that shape actually is, it has to be the absolute min. And the converse is also true. If you're increasing everywhere to the left and decreasing everywhere to the right, then that has to be an absolute max. All right. So this is a fun one. I like this. Find the point on the parabola that is closest to this point. Y squared equals 2x. Why not? Closest to the point 1, 4. This is an optimization problem, but it's not really applied. It's not got anything to do with the real world, but we're still trying to minimize or maximize something. So I'd like to find the point on this sideways parabola that is closest to 1, 4. You could make a table of values or use what you remember about conic sections from pre-calculus to get the graph of y squared equals 2x. It looks the same as y equals 1/2 x squared, just flipped sideways. The vertex is at the origin, opens to the right. the point 1, 4, square root of 2. So 1, 4 is way up here. And I'd like to know what point on the parabola is closest to that. Like here, the distance is this. Here, the distance is this. Here, the distance is this. And you can see that these two are definitely further from 1, 4 than this guy. My sweet spot is somewhere in here, but I'd like to know exactly where. So in general, how do we find the distance between a point on this curve and the point 1, 4?
Distance formula.
Yeah, remember the distance between any 2 points I'll say x1, y1 and x2, y2 satisfies d squared equals y2 minus y1 squared plus x2 minus x1 squared. Oftentimes you'll see this written in the square root, right? You take the square root of both sides and you get d. But for the purposes of calculus, it's often nicer to think of it like this. A point along the graph y squared equals 2x. Well, if this is an arbitrary x value, then this would be x, and y would be the square root of 2x. Or maybe the negative square root of 2x if we're down here. But this is what an arbitrary point looks like on here. So x1, y1 are 1 and 4. x2, y2 are x and square root 2x. So the distance from a point on the parabola to 1, 4, it satisfies d squared equals, here's y1, here's x1, here's y2 and x2. So this would be 4 minus square root of 2x squared plus x2 minus x1, that would be 1 minus x squared. There are other ways to do this. I want to be clear about that. You can swap the points. I called this one x1, x2, y2, and this one x1, y1. You could swap the role of those. That wouldn't change anything. You could characterize an arbitrary point on the graph in terms of the variable y as, what would we do there? That would be y in the y component, and then here you'd have to solve for x. It'd be y squared over 2. But this, I think, is the most natural way. So I want to minimize the function d. To do that, I'm going to differentiate through here implicitly. And I get 2d times d prime on the left. On the right-hand side, I'll get 2 times 4 minus the square root of 2x times the derivative of the inside here. The 4 differentiates to 0. The square root of 2x, that requires the chain rule. That's 1/2 2x to the negative 1/2 times 2 plus 2 times 1 minus x times negative 1. Oh, this should also be negative, sorry, because we're subtracting inside there. All right, so there's quite a bit of chain rule stuff going on here. I can divide everything by 2. These will go. And I get that d times d primed is equal to, within here I can cancel this 2 and this 1/2. And I get 4 minus square root of 2x times 2x to the negative 1/2. That's over the square root of 2x minus, or we could say plus 1 minus x times negative 1. I'll write it as minus 1 minus x, like this. Now I'm going to have a common denominator on the right-hand side. Eventually I'll divide over by d. D times d primed here. I'll multiply by 2 root x over 2 root x. Or sorry, root 2x. So I'll get 4 minus root 2x over root 2x minus 1 minus x root 2x over root 2x. And now I can put these together into a single fraction. Upstairs here, we can distribute this and then subtract, and we'll see what we get. So d times d primed is 4 minus the square root of 2x. I'll have minus 1 times the square root of 2x, so that's minus the square root of 2x, minus negative x times root 2x, so that's plus x square root 2x, all over the square root of 2x. So what do I get here? This is 4 minus 2 square roots of 2x plus x square roots of 2x all over the square root of 2x, which means that d primed is this divided by d. Now that distance is never 0. Just from looking at the picture, we know that the distance between the point 1, 4 and any point along this graph is never 0. So that's why I did the differentiation implicitly, so I don't have to worry about the d downstairs there. I didn't need to invoke all the nasty chain rule things that we might have to invoke. But figuring out when this numerator is 0, that's still no small chore. So I'm going to come back here and make sure I didn't goof anything, but I think this is correct, and we just need to solve when this top is 0. Unfortunately, that's not an easy thing to do. So we differentiate this, we get that, times the derivative of that, which is definitely 1/2 this to the negative 1/2 times 2 by the chain rule. And I was thinking these things would cancel, but they are not. Yeah, no, okay. So we got to figure out where this thing is 0. So critical numbers. come when d primed equals 0 or d primed is undefined. D prime is undefined when x is 0 or d is 0. D is never 0, so we don't need to worry about this. We know that that curve does not go through the point 1, 4. It's undefined when x is 0, so we have to hold on to that. That is a critical number. But what about when the top is 0? This is going to be what will actually give us our solution. This is quite challenging. 4 minus 2 square roots of 2x plus x square roots of 2x is equal to 0. And I'm trying to look at this thinking of things we can do. But if I'm honest, it's not jumping out at me. It's not a polynomial equation. We certainly can't get there by like factoring this, at least not right away. We could try squaring both sides, but that's not going to do everything either. We'll still have cross terms. We could make a substitution. I think that's going to be the way to do this. If I substitute u as the square root of 2x, then u squared is 2x, or 1/2 u squared is x. So this is the same as saying 0 equals 4 minus 2u plus 1/2 u squared times u. And this now at least is a polynomial equation we can hope to solve. We get 0 equals, I'll multiply everything by 2, so we get 8 minus 4u plus u cubed. That's still quite tricky. This is a degree 3 polynomial. We could jump in with the rational roots theorem, but I think we're going to run out of time before I'm able to resolve this. So I'm sorry to do that. I suspect this means that there was, if you go in terms of y, it's much nicer. So what I did is I came to this equation, y squared equals 2x, and I solved it for y. So that we had this expression for the distance. I was thinking working in terms of the variable x might be nicer. However, if we'd gone back and worked in terms of the variable y instead, then that would have been much nicer. So I actually took us down a nasty, nasty path. Well, I'll tell you what. I will pick this up here on Friday. I'll come back and we can finish solving it like this. I'll give you at least a quick breakdown of how the solution could continue from here. And then we'll solve it the cleaner, faster way by working in terms of the variable y. The move from here is to use the rational roots theorem to extract a rational factor, a linear factor from this, and then factor the resulting quadratic. But it's just nasty. So this all could have been done much better by instead thinking about y squared equals 2x. The points along this, you can think of them as x comma the square root of 2x, or you could think of them as y squared over 2 comma y. I chose to go with this characterization, which led us to a really nasty algebra problem. But if you go with this characterization, then everything is much nicer. So if you want to finish this, I'll show you how you would sort it out. Otherwise, we will do it together on Friday. Here, d squared, the distance squared, would be y2 minus y1, or maybe it would be 4 minus y squared plus x2 minus x1, 1 minus 1/2 y squared squared. And so 2d times d primed would be 2 times 4 minus y times -1 plus 2 times 1 minus 1/2 y squared times the derivative of the inside here, y squared differentiates to 2y, so this would just be y. And then the process from here is easier. You divide both sides by 2, the 2's all go. D primed would be y minus 4 plus 1 minus 1/2 y squared times y all over d. And setting this to 0 is going to be a hell of a lot easier than setting this to 0. But I'll go through this more slowly, more gently as our first problem on Friday during the review, and I'll ask that you guys bring questions from the study guide, from the homework, wherever you want, whatever you want to work on for Friday. That is it. I will let you guys go here because I have another class starting in just a minute. Sorry that this last problem got a little gnarly, but there's a teachable moment here. So if you're setting up a problem and you start encountering nasty, nasty algebra stuff, it's worthwhile to go back and consider if there's another way to set it up. Indeed, in this case, by focusing on y as the variable instead of focusing on x as the variable, we could have given ourselves a much gentler approach to the solution. All right, so I'm going to stop the lesson here for today. I hope you guys have a lovely rest of your day. If you get stuck on anything, as always, please send me a Canvas message or come to office hours. I have my normal office hour this afternoon from 3:30 to 4:30. Tomorrow, Thursday, I will actually be doing an in-person office hour in A025, which is right next to my office, A31, from 9:45 to 11. But then after that, I'm going to go vote. And depending on how long the early voting lines are at my polling place, I may not be back in time for my regular Tuesday, Thursday office hour. So tomorrow's online office hour might be a little bit late. I'll post an announcement letting you know. But if you want to, you can come to the in-person office hour at 9:45 also. All right, take care, guys. I will see you next time.